In the next 72 hours, space experts will be watching the Sun with unusual care. A quiet-looking star can send out radiation, plasma, and magnetic disturbances that reach far beyond its surface, crossing space and pressing against Earth's magnetic shield. Most people will never see this process unfold, but its effects can reach satellites, signals, auroras, and even power systems on the ground. In this video, the story follows that chain step by step, from the Sun to Earth. In calm detail, please like, subscribe, and share the video to support the channel and stay with the next deep journey into science. Far from Earth, the Sun presents a bright and nearly steady face. At a distance of about 150 million kilometers, it appears simple enough to the unaided eye when filtered through proper instruments. A round source of white light, smooth in outline, constant in presence, and ancient in rhythm. Yet under close observation, that bright face is never truly still. Its visible surface, called the photosphere, is not a solid shell. It is a layer of glowing gas where light escapes after a long outward passage from the deep interior. What appears calm from a distance is in fact a shifting field of heat, motion, and magnetism. Space experts begin here because every later concern in the coming 72 hours depends on what is already visible on this outer face. Across the photosphere, hot gas rises from below, cools, and sinks again. This overturning motion creates a pattern known as granulation. A granule is a small cell of rising hot gas bordered by darker lanes where cooler gas falls. Through solar telescopes, the surface resembles a broad plane of bright, irregular grains that form and fade over minutes. Each cell is large by human measure, often spanning hundreds to more than 1,000 kilometers. Yet on the Sun they are part of a fine texture spread across an immense sphere. This texture matters because it reveals that the visible surface is active even in its quietest state. Heat is moving upward everywhere. Energy is constantly arriving at the surface and passing outward into space as light. The Sun rotates, though not as a rigid body. Its equatorial regions turn faster than its higher latitudes. Over days, careful observers track subtle movement in surface features and see that the star is always changing. This uneven turning slowly twists magnetic fields rooted in the solar gas. Magnetism on the Sun is not fixed in place like iron bars in a machine. It is carried, stretched, folded, and concentrated by moving plasma, which is hot gas whose particles are charged and therefore respond strongly to magnetic forces. This link between plasma and magnetism explains why the Sun's surface is watched so closely when experts speak in cautious terms about the next 72 hours. The visible face gives the first broad signs that magnetic stress is building or relaxing. Among the most noticeable features on the photosphere are sunspots. A sunspot appears dark against the surrounding surface, not because it is cold in an absolute sense, but because it is cooler than nearby regions. The surrounding photosphere glows at about 5,500 degrees Celsius. A sunspot is cooler by roughly 1,000 to 2,000 degrees Celsius, so it emits less visible light and appears dark by contrast. A large sunspot group can be wider than Earth. Within a mature spot, a darker central region called the umbra is often surrounded by a lighter ring called the penumbra, where magnetic fields spread outward in filament-like patterns. These dark features mark areas where magnetic fields become especially strong and concentrated, partly suppressing the normal upward flow of heat. Sunspots do not appear at random in a simple sense. They often form in pairs or groups, reflecting loops of magnetic field that rise from below the visible surface. One part of the loop emerges through the photosphere, and another part re-enters it nearby. The result is a connected magnetic region with opposite magnetic polarity in different spots. During active periods of the solar cycle, many such groups can appear across the solar disk. During quieter phases, the visible face carries few or none. The solar cycle itself lasts about 11 years in the familiar rise and fall of sunspot numbers, though the deeper magnetic cycle is longer because the polarity pattern reverses and later returns. Experts do not treat every active region as a cause for alarm. Most produce little that affects Earth in a serious way. What matters is the structure, size, complexity, and change over time of these regions. Complexity is important because tangled magnetic fields can store energy. On solar images, some active regions look simple and well separated. Others appear crowded, twisted, and mixed, with bright patches and tightly packed spot groups in which opposite polarities lie close together. These are the regions that receive closer attention. Space weather forecasters study daily magnetograms, which are maps of magnetic direction and strength on the sun's surface. They compare these maps with white light images of sunspots and ultraviolet views of the overlying atmosphere. Even without leaving the visible surface, they can already see hints of strain. When a region grows quickly, when spots become more numerous, when boundaries between opposite magnetic areas sharpen or stretch, concern rises in a measured way. The visible face also shows bright regions around active sunspot groups. These bright patches, often called faculae, are magnetic areas that stand out especially well near the edge of the solar disk. They indicate strong surface fields even when spots are small or absent. Their presence reminds observers that the sun's face cannot be judged by darkness alone. A region may carry important magnetic structure without forming the most dramatic sunspots. In this way, the photosphere serves as a map of conditions at the threshold between deeper solar motion and the layers above. It does not yet reveal every outcome, but it offers the first grounded basis for watchfulness. When experts warn about a coming span of hours rather than speaking in general terms, they are often responding to changes that can be timed. An active region rotates into view from the eastern edge of the sun. A spot group grows larger over 1 or 2 days. The magnetic pattern becomes more disordered. New flux emerges, meaning new magnetic field rises through the surface from below. Surface motions shear the region, drawing opposite fields past one another. None of this guarantees a major event. Observations indicate that some complex regions remain quiet, while others release energy suddenly. It remains uncertain in any single case exactly when stored magnetic energy will be released, or whether it will be released in a way that matters for Earth. That uncertainty is normal and central to responsible forecasting. The sun's visible surface therefore becomes a place of close patience rather than dramatic certainty. Solar observatories on Earth and in space return continuous images. Analysts compare present frames with earlier ones. They note whether a region is stable, whether penumbral structure is changing, whether new pores and spots are appearing, whether the area is broadening, and whether the magnetic arrangement is becoming more complex. This work is quiet and methodical. It resembles weather watching in one sense, though the medium is plasma and the forces are magnetic. The visible disk is the first outward region where the long chain of events can be tracked in a direct way. In this calm light, the phrase warning about the next 72 hours does not mean panic. It means that the sun's surface is showing patterns that deserve sustained attention over a defined interval. The photosphere, bright and seemingly placid, carries these signals plainly enough for trained observers to read them. Dark spots mark magnetic concentration. Fine granules show constant convective motion. Bright faculae outline field-rich zones. Rotation brings new regions into view and carries old ones toward the far side. Across this shining layer, experts watch for the balance between ordinary change and unusual strain. The first region in the story is therefore not violent in appearance. It is luminous, textured, and restless in a controlled way. A visible skin of a star whose deeper motions right themselves briefly in light. Above the sun's bright visible surface lies a region that does not look dense or solid, yet reaches far outward and holds much of the tension that concerns space experts. This is the corona, the sun's outer atmosphere. During a total solar eclipse, it appears as a pale halo extending into the darkened sky, delicate in outline and uneven in form. In ordinary light, it is hidden by the overwhelming brightness of the photosphere, but special instruments reveal it as a vast atmosphere of extremely thin plasma shaped by magnetic fields. It is in this outer region that heat, motion, and magnetic structure become easier to trace, and it is here that observers begin to see how a quiet-looking surface may support unstable conditions above it. The corona is hotter than the visible surface below. This is one of the long-studied problems of solar science. The photosphere glows at about 5,500 degrees Celsius, yet the corona reaches temperatures of more than 1 million degrees Celsius in many regions, and in some places even higher. Observations indicate that magnetic processes are central to this heating. The exact balance of mechanisms remains uncertain, but two broad explanations continue to guide research. One is that waves generated by motion lower down carry energy upward and release it in the corona. Another is that many small magnetic reconnection events heat the plasma. Reconnection is the process in which magnetic field lines change their connections and release stored energy. In either case, the corona is not a passive shell. It is an active and heated outer atmosphere where magnetic forces organize the movement of matter. Because the coronal plasma is so thin, it does not behave like the dense air near Earth's surface. Individual particles travel under the strong influence of magnetic fields, and the atmosphere takes on forms that follow invisible magnetic paths. Solar images in ultraviolet and X-ray wavelengths show loops, arcs, streamers, and bright knots suspended above active regions. These shapes are not solid structures. They are glowing traces of hot plasma confined by magnetic fields. A coronal loop is a curved arch of plasma rising from one magnetic footpoint on the solar surface and descending into another. Some loops are short and low, others rise high into the corona. Their brightness depends on density and temperature, and their changing form can show whether magnetic conditions are stable or evolving. Above quiet parts of the sun, the corona may appear more open and diffuse. Above active regions, it often becomes crowded with bright loops crossing in many directions. When viewed over hours or days, these loops brighten, fade, expand, and rearrange. Some movements are gradual, others occur quickly. Space weather experts study these patterns because they reveal where magnetic energy is being stored. A loop that seems smooth and steady may simply be holding hot plasma in place. A loop system that becomes increasingly sheared or twisted may indicate stronger stress. Shear means that magnetic footpoints on the surface move past one another, distorting the field above. Twist means the field becomes wound around itself. These changes do not guarantee a major eruption, but they increase scientific interest because the corona is where surface magnetic complexity becomes three-dimensional structure. Large darker regions in coronal images also draw attention. These are coronal holes, areas where the magnetic field opens more directly into space rather than closing back down in loops nearby. Because the plasma density is lower and the temperature structure differs, These regions appear dark in certain wavelengths. Coronal holes are important because they are sources of faster solar wind, the continuous outflow of charged particles from the Sun. In the present region of the story, however, the focus remains on the atmosphere itself rather than on the flow far beyond it. What matters here is that the corona is not uniform. It contains closed magnetic zones, open magnetic zones, bright active structures, and broad, faint streamers that extend outward. Each pattern reflects a different magnetic arrangement. The corona is shaped by the Sun's magnetic field on many scales at once. Small loops connect nearby patches of opposite polarity. Larger loop systems span wide active regions. At even larger scales, streamers rise high above the surface and trace the broader solar magnetic environment. In white light coronagraph images, which block the bright solar disk and reveal the faint outer atmosphere, these streamers can appear as long tapered forms reaching millions of kilometers into space. Their slow changes help observers understand the background state of the Sun. Yet the corona can also change suddenly. Brightening in one active region, expansion of loop systems, or the appearance of a rising structure can all indicate that magnetic balance is shifting. One important coronal structure is the filament channel, often associated with cooler material suspended above the surface by magnetic fields. When seen against the bright solar disk, this material appears dark and is often called a filament. When seen at the edge of the Sun extending outward, the same kind of feature is called a prominence. Although the material is cooler than the surrounding corona, it remains extremely hot by ordinary standards. These long dark bands may persist for days or weeks. Their presence shows that the corona can support dense plasma against gravity through magnetic structure alone. Sometimes these features remain stable, sometimes they rise, distort, and disappear from their original position. In such cases, observers know that magnetic support has changed. Whether that change ends quietly or leads to a larger release of energy depends on conditions that the corona itself helps reveal. This outer atmosphere is also where time becomes especially important. A surface region may look complex, but the corona shows whether that complexity extends upward into stressed loops and unstable arcades. An arcade is a set of loop-like structures standing side by side above a magnetic boundary. If the arcade remains broad and settled, concern may stay limited. If it becomes sharply sheared, brightens repeatedly, or forms a rising cavity above a filament, closer watch begins. Forecasters examine sequences of images rather than single frames. Motion matters as much as shape. A slow inflation of loops over several hours may indicate increasing magnetic pressure. Repeated small brightenings can suggest ongoing reconnection in a stressed region. Still, observations alone do not always yield certainty. Some coronal systems appear strained and do not erupt. Others change little before releasing energy rapidly. The corona therefore becomes a place where uncertainty is disciplined by measurement. Solar observatories record multiple wavelengths, because different wavelengths reveal plasma at different temperatures. Cooler coronal material appears in one set of channels, hotter plasma in another. By comparing them, analysts infer where heating is concentrated, where plasma is draining or rising, and where magnetic change may be underway. Coronagraphs extend the view farther outward and show whether material is already moving into the outer corona. Magnetically sensitive measurements from the surface provide the lower boundary, while the corona reveals the architecture above it. Together they allow experts to judge whether the outer atmosphere is simply active in an ordinary way, or whether it is entering a more strained state over the next 72 hours. Seen from afar, The corona is faint and beautiful, almost weightless in appearance. In scientific practice, it is a structured and dynamic region that holds the sun's magnetic tension in visible form. Hot loops trace field lines across active regions. Streamers rise into space. Dark coronal holes mark more open magnetic paths. Filaments rest within delicate balances that may persist or fail. The outer atmosphere carries the signs of stored energy not as noise, but as pattern. For this reason, experts continue to watch it with quiet concentration. The corona does not yet send anything toward Earth in this section. It simply reveals the condition of the sun's outer atmosphere, where heat remains high, matter remains thin, and magnetic structure shapes almost everything that can be seen. From the structured outer atmosphere of the sun, attention settles on the moments when stored magnetic energy is no longer contained in place. In this region of the story, the focus is on flares and coronal mass ejections, two related but distinct expressions of solar unrest. Both begin in the sun's magnetic environment, and both matter because they can affect space far beyond the star itself. Yet they are not the same event. A flare is a sudden release of energy, seen mainly as an intense burst of radiation across many wavelengths. A coronal mass ejection is a large expulsion of solar plasma and magnetic field into space. They often occur together, but either can happen without the other. Experts separate them carefully because each one moves outward in a different way and creates a different timing of effects. A solar flare begins when magnetic fields in the corona reach a point where their configuration changes rapidly. The process called magnetic reconnection is central here. In reconnection, magnetic field lines that have been forced into a strained arrangement break and reconnect in a new pattern. This change releases stored magnetic energy into heat, motion, and radiation. The surrounding plasma becomes much hotter, and particles can be accelerated to high energies. In observations, the flare appears as a brightening that can rise quickly in intensity and then fade over minutes to hours. The event is often strongest in X-rays and ultraviolet light, though its effects are recorded across a wide span of the electromagnetic spectrum. At the visible surface below a flare, bright ribbons may appear on either side of a magnetic boundary. These flare ribbons mark places where energy carried downward from the corona heats the lower atmosphere. Above them, loops fill with hot plasma and brighten strongly. What had been a tense magnetic arrangement becomes, for a time, a changing pattern of newly connected structures. The pace may seem sudden by solar standards. A region that looked only mildly unsettled can brighten sharply in a short interval. Instruments register the increase in radiation almost immediately. For scientists watching the next 72 hours with care, this is one of the key changes that can shift a period of general concern into a period of active response. Flares are classified by the strength of their soft X-ray output. The categories rise from smaller events to much stronger ones, with the largest class known as X-class. Within each class, numerical levels give further detail. This classification helps forecasters compare one event with another, but it does not by itself describe the full effect on Earth. The direction of associated material, the magnetic structure involved, and the condition of interplanetary space also matter. A strong flare may occur on a part of the Sun not well connected to Earth in a direct way. A more moderate event may still produce noticeable consequences if other conditions align. For this reason, experts treat the flare as one measured part of a larger chain rather than as a complete answer. Radiation from a flare travels at the speed of light. This means that the first effects of a major flare reach Earth in a little over 8 minutes, the time needed for light to cross the distance between the Sun and Earth. These first effects do not involve dense clouds of matter. They involve high-energy radiation, especially X-rays and extreme ultraviolet light, which interact with Earth's upper atmosphere and ionosphere. In the present section, however, the focus remains close to the Sun itself, on the source event and on the difference between radiation release and the larger outward motion of plasma. This distinction is essential. A flare is the flash of released energy. A coronal mass ejection is the broad launch of solar material. The coronal mass ejection, often shortened to a large solar eruption of plasma, begins when part of the coronal magnetic structure loses stability and rises outward. This may involve a filament eruption, a rising magnetic flux rope, or a broader destabilization of overlying loops. A flux rope is a bundle of twisted magnetic field lines containing plasma. Observations indicate that many coronal mass ejections involve such structures, though not every detail is directly visible before eruption. As the structure rises, it pushes against surrounding magnetic fields. Reconnection below it can add more energy and help release it fully into space. In coronagraph images, the event may appear as a bright expanding front, followed by a darker cavity and a brighter inner core. This classic three-part structure is not always perfectly visible, but it provides a useful picture of how some eruptions unfold. The amount of matter carried outward can be enormous, reaching billions of tons of plasma. Speeds vary widely. Some ejections move relatively slowly and blend into the background solar wind. Others race outward at more than 1,000 kilometers per second. And the fastest may move much faster still. Speed matters because faster ejections are more likely to drive shocks through the surrounding solar wind. A shock in this sense is a sharp disturbance that compresses plasma and magnetic fields ahead of the moving eruption. Such shocks can accelerate energetic particles and alter the conditions through which the ejection travels. Yet even here, not every strong-looking eruption becomes a major Earth-directed event. Direction is critical. An ejection aimed away from Earth may be spectacular in solar images and still have limited direct consequence for the planet. Experts therefore ask several quiet questions as soon as a flare or ejection begins. They ask where on the Sun the event occurs, how broad the eruption appears, how fast it is moving, whether a halo forms around the occulted solar disk in coronagraph images, and whether the associated magnetic region had been growing more complex. A halo coronal mass ejection appears to spread around the blocked disk in a circular or partial circular form, suggesting that material is moving toward or away from the observer. From the vantage point of Earth-orbiting spacecraft, a halo event can indicate that the eruption has a strong earthward component. Even so, confirmation takes time. The apparent shape depends on viewing angle, and a full understanding often requires multiple instruments and modelling. The relation between flares and coronal mass ejections remains close but not identical. A flare may brighten intensely while only a modest amount of plasma escapes. A large ejection may develop with only moderate flare emission. In many major eruptive events, however, the two unfold together as different aspects of one magnetic reorganization. The flare marks rapid release of energy into heat, light, and accelerated particles. The ejection marks the outward removal of plasma and magnetic structure from the corona. Together they transform a once strained region into a changed one. Loops below may settle into a less stressed arcade. Material above moves away into interplanetary space. The Sun's outer atmosphere, which in the earlier section held tension in visible form, now releases part of that tension into motion and radiation. This region of the story remains near the source. It does not yet follow the eruption across space or into Earth's environment. It stays with the moment when solar instability becomes outward action. Instruments on spacecraft and ground-based observatories register the burst, the brightening, the expansion, and the first estimates of speed and direction. Analysts compare image sequences frame by frame. They note whether the eruption is narrow or broad, whether it rises cleanly or asymmetrically, whether the flare ribbons spread, and whether post-eruption loops brighten below the departing structure. These details shape the forecast that follows. In this way, flares and coronal mass ejections become the turning point between solar tension and space weather consequences. They are neither mysterious flashes nor abstract warnings. They are measurable events in a star's magnetic atmosphere, driven by reconnection, heating, and the outward release of plasma. What has been stored in the sun's fields is now leaving its place of origin. The bright release and the expanding cloud are the first direct expressions of that change, and they mark the moment when close solar watching becomes a matter of wider space attention. Once a flare occurs, the first part of its influence does not wait for matter to cross the space between Sun and Earth. It arrives as radiation, moving outward at the speed of light. This is the earliest outward region after the source itself, and it is the reason the first phase of concern in a 72-hour interval can begin almost at once. Light from the Sun already takes a little more than 8 minutes to reach Earth. The additional radiation from a flare follows the same path and the same timing. In this region, space is not yet filled with a moving cloud of solar plasma. Instead, it is crossed by a sudden increase in X-rays, extreme ultraviolet light, radio emission, and, in some events, energetic particles that begin to stream outward along magnetic pathways. Radiation is a transfer of energy through electromagnetic waves. In a flare, the Sun releases more energy than usual across a broad range of wavelengths. Some of this energy is visible only to specialized instruments. Soft X-rays rise sharply during the flare and are used to classify its strength. Extreme ultraviolet radiation also increases and can alter the upper parts of Earth's atmosphere soon after arrival. Radio bursts may occur as electrons move through the Sun's outer atmosphere and interplanetary space. These emissions allow scientists to identify not only that a flare has taken place, but also how the event is unfolding in time. A flare has a beginning, a rise, a peak, and a decline, and each stage can be measured with high precision. The space between Sun and Earth is often imagined as empty. In this part of the story, it is better understood as open but not vacant. It contains magnetic fields, streams of charged particles, and faint plasma from the solar wind. Through this medium, radiation passes with little delay, carrying the first outward signal that magnetic energy has been released at the Sun, because the travel time is so short. This first signal is often the earliest direct warning that conditions near Earth may soon become more disturbed. It does not by itself guarantee a severe geomagnetic storm later on, because that depends more strongly on the arrival and magnetic structure of a coronal mass ejection. Still, the radiation phase matters in its own right. It marks the beginning of a measurable sequence that can affect radio communication and upper atmospheric conditions long before any denser solar material arrives. One important distinction in this region is between electromagnetic radiation and solar energetic particles. Radiation crosses the Sun-Earth distance in minutes. Energetic particles, if accelerated efficiently by the flare or by a shock associated with an erupting coronal mass ejection, take longer. Their travel time can range from tens of minutes to many hours, depending on their energy and the magnetic pathways available to them. A solar energetic particle is a proton, electron, or heavier ion that has been accelerated to high speed. These particles do not move straight through space in the way light does. They follow magnetic field lines, scatter, and spread through the interplanetary medium. Even so, the fastest among them can arrive relatively early, which is why the opening phase of a solar event involves more than a simple flash of light. Not every flare produces a strong particle event. Observations indicate that the most substantial particle storms are often linked to fast coronal mass ejections that drive shocks through the solar wind. These shocks can continue to accelerate particles as they move outward. In some cases, particles accelerated near the flare site itself also contribute. It remains uncertain in specific events how much comes from the flare region and how much from the outward moving shock. But both processes are grounded in measured physics. What matters in this region is that the first wave across space may include both radiation and early fast particles, and these arrive well before the main body of any coronal mass ejection. As this radiation travels outward, monitoring systems respond quickly. Spacecraft between Sun and Earth, and spacecraft in near-Earth space, record-changing X-ray levels, radio signatures, and rising particle counts. Forecast centers compare these real-time measurements with earlier solar images and model expectations. If the flare is strong and the source region lies in a position that connects well with Earth through the Sun's magnetic field, concern about energetic particles grows. If the flare appears strong in radiation but the geometry is less favorable, attention may shift more toward later phases. This is why experts speak carefully. The first wave is informative, but it is only one part of the event. In the broad open distance from the Sun, magnetic connection matters. The Sun's magnetic field, carried outward by the solar wind, does not form straight spokes. Because the Sun rotates while the solar wind flows outward, the field takes on a spiral pattern. This means that some solar regions connect more directly to Earth's part of interplanetary space than others. When energetic particles are released into a well-connected magnetic path, they can reach Earth more efficiently. When the connection is poor, many particles spread elsewhere. This geometry cannot be seen directly in a simple image, but it is inferred from models, in situ measurements, and the position of the solar source region. In this way, the first outward wave is shaped not only by the power of the flare, but also by the architecture of space between Sun and Earth. The radiation itself does not carry mass in the same sense as a plasma cloud, yet it has immediate physical effects. X-rays and extreme ultraviolet light can ionize atoms and molecules in Earth's upper atmosphere, meaning they remove electrons and increase the number of charged particles there. These changes happen rapidly on the sunlit side of Earth. In this section, however, the focus remains on the crossing of space rather than the atmospheric response at Earth. The important point is that the first effects on Earth do not wait for the slower movement of plasma. They begin with this swift transfer of energy through open space. The 72-hour interval that experts watch so carefully often begins with these minutes and hours of rapid transit. The source event at the Sun has already occurred. Now the evidence of that event spreads outward. Instruments measure light curves, particle counts, and radio signatures. Analysts determine whether the flare has ended cleanly, whether particle flux is rising, and whether additional bursts follow from the same active region. Multiple flares in close succession can complicate interpretation, especially if each one contributes radiation or particles to an already disturbed environment. Even then, the same basic rule holds. Radiation is first. It is the opening signal that leaves the Sun and reaches Earth with almost no delay on human timescales. This region of the story therefore remains thin, open, and fast. It is the domain of the first wave, when the consequences of solar activity begin to spread without waiting for the larger cloud behind. Through the interplanetary medium, X-rays and ultraviolet light move swiftly. Radio bursts mark the event, and the earliest energetic particles may begin their journey along magnetic spirals. Space experts watch this passage not because it tells them everything, but because it tells them that the event is no longer confined to the Sun. The warning has entered space between worlds, and the long distance is already being crossed. Beyond the first wave of radiation, the space between Sun and Earth is filled by a steadier and more persistent flow. This is the solar wind, the continuous outflow of charged particles from the Sun's outer atmosphere. In this region of the story, attention rests on that long stream itself, because any later disturbance must travel through it. The solar wind is not an empty backdrop. It is the medium that carries magnetic fields outward from the Sun, shapes the path of eruptions, and determines how energy and matter spread across interplanetary space. When space experts warn about the coming 72 hours, they're not thinking only about what has left the Sun. They're also thinking about the conditions of the stream through which it now moves. The solar wind begins in the corona, where the Sun's outer atmosphere is hot enough and extended enough that particles can escape the Sun's gravity. This outflow is made mostly of protons and electrons, with a smaller amount of helium nuclei and trace heavier ions. Because the gas is ionized, it is plasma. The Sun's magnetic field is carried outward with it. In this way, the solar wind is both a flow of matter and a moving magnetic environment at Earth's distance. This flow is still thin beyond ordinary comparison, yet it is strong enough to shape planetary magnetic shields, compress the boundary of near-Earth space, and transmit disturbances across millions of kilometers. The solar wind does not move at one fixed speed. Broadly, there is slower wind and faster wind. Slower wind often travels at about 300 to 500 kilometers per second. Faster wind may reach about 600 to 800 kilometers per second, and sometimes more. These numbers vary, and the wind changes from day to day and even hour to hour. Fast streams are commonly associated with coronal holes, where magnetic fields open more directly into space. Slower wind is often linked to more complex magnetic regions near the boundaries of closed and open fields. This difference matters because the background speed of the solar wind influences how a coronal mass ejection expands, slows, or interacts with the surrounding medium on its way outward. As the solar wind leaves the rotating Sun, it does not form straight radial lines in a simple permanent pattern. Because the Sun turns while the wind flows away, the embedded magnetic field is drawn into a spiral shape in interplanetary space. This broad pattern is often called the Parker spiral, after the scientist who first described the solar wind theoretically. The result is that magnetic connection between Sun and Earth depends not only on distance, but also on geometry. An eruption that occurs in one part of the Sun may couple more directly into Earth's region of space than another eruption of equal strength in a less favourable position. The solar wind therefore acts not just as a carrier, but as an organizer of connection. The solar wind also contains variations in density, temperature, and magnetic field direction. Density tells how many particles are present in a given volume. Sometimes the wind is relatively sparse, sometimes it is denser, carrying more material through the same region of space. Its magnetic field also changes direction and strength over time. These changes are not minor details. They influence how strongly Earth's magnetic environment may react when disturbed solar material arrives. If the background magnetic field in the solar wind is aligned in certain ways before a major eruption reaches Earth, the interaction that follows can be either moderated or strengthened. This is why forecasters look not only at the Sun and the eruption, but also at upstream measurements of the solar wind itself. A coronal mass ejection moving away from the Sun does not pass through still air. It moves through this flowing plasma stream. If the ejection is faster than the background wind, it can plow into the plasma ahead of it and create a shock. That shock compresses the solar wind and alters the magnetic field in front of the main cloud. If the eruption is slower, it may be carried outward more gently, shaped by the flow around it. Sometimes fast wind from a coronal hole follows behind a slower ejection and changes the way it evolves. Sometimes two eruptions leave the Sun close together in time and interact with each other in transit. In such cases, the solar wind path becomes more complex, and the exact timing and structure of arrival near Earth become harder to determine. This interplanetary region is watched through spacecraft positioned between the Sun and Earth, as well as by model calculations that project the motion of solar plasma outward. Analysts ask how fast the eruption appears to be moving, how wide it is, and what kind of solar wind lies ahead of it. They compare model outputs with observations from heliospheric images and in situ monitors when available. These measurements do not eliminate uncertainty. A coronal mass ejection expands as it travels. Its speed changes. Its shape may tilt or distort. The solar wind around it may speed up or slow down unevenly. Observations indicate general trends, but it remains uncertain in many cases exactly how the internal magnetic structure will evolve before reaching Earth. Even without a major eruption, the solar wind itself can produce important effects. High-speed streams from coronal holes can interact with slower wind ahead of them and form compressed regions called co-rotating interaction regions. These are broad zones where density and magnetic field strength increase, because faster plasma catches slower plasma. Such structures can disturb Earth's magnetic environment and sometimes produce moderate geomagnetic activity. In the present 72-hour window, this background may already be active before any new eruption arrives. That possibility matters because a fresh coronal mass ejection entering an already disturbed solar wind can produce a more complicated sequence of effects than an isolated event in quiet conditions. Time across this region is no longer measured in minutes. As it is for radiation, it is measured in many hours to a few days. A fast eruption may reach Earth in less than 2 days. A slower one may take closer to 3 days or more. This is why the phrase next 72 hours is scientifically meaningful. It matches the travel times of many interplanetary disturbances moving through the solar wind from Sun to Earth. During this interval, forecasts are updated repeatedly. Early estimates of arrival can shift by many hours as better observations and improved models refine the picture. Experts therefore avoid claiming exact certainty too early. They present ranges, confidence levels, and likely scenarios grounded in the measured speed and path of the disturbance through the solar wind. In this long stream between worlds, the visual drama of the solar eruption is replaced by quieter motion. There is no bright flash here, only plasma moving through plasma, fields carried through fields, compression, expansion, and gradual change over vast distances. Yet this quiet region is one of the most important in the whole chain. It determines how the original solar event is transformed before it reaches Earth. It can speed up the warning or delay it. It can sharpen the front of a disturbance or allow it to broaden. It can carry energetic particles efficiently or scatter them more widely. The solar wind path is therefore not merely the road between the Sun and Earth. It is part of the event itself, its speed, density, and magnetic direction shape the form of what arrives. Its spiral field determines how early particles may connect to Earth. Its changing background decides whether an eruption travels cleanly or interacts with older streams and structures already in space. In this outer interplanetary region, the first clear movement from the Sun becomes a journey through a living medium. The warning continues outward not through emptiness, but through a flowing, magnetized stream that fills the distance all the way to Earth. Earth now comes into view not as a landscape of oceans and clouds, but as a small planet moving through open space within the Sun's constant outflow. At this distance, the familiar world is part of a larger physical setting. It travels around the Sun at about 30 kilometers per second while turning on its axis once each day, and all the while it remains embedded in a stream of solar plasma and magnetic field. Seen in this way, Earth is not separate from space weather, it is immersed in it. The warning about the next 72 hours gains meaning here because the planet is neither fixed nor sheltered by emptiness alone. It occupies a moving position inside a changing interplanetary environment. From far away, Earth reflects sunlight and appears bright against black space. Its atmosphere forms a thin, luminous rim when backlit. The Moon circles nearby as a smaller companion. Artificial satellites surround the planet in many orbital paths, though at this scale they are too small to be seen individually. The whole system moves through a region shaped by the solar wind. That wind flows past Earth continuously, carrying charged particles and magnetic fields from the Sun. Most of the time, this passage is steady enough that life at the surface notices nothing directly. Yet the planet does not stand outside the flow. It is a physical object in a dynamic stream, and the first question for experts is simple. What exactly is approaching, and how directly will Earth meet it? The answer begins with scale. Earth's diameter is about 12,700 kilometers, which is large in human terms and very small by the measure of interplanetary space. The distance from the Sun to Earth is so great that a major solar eruption can spread enormously before it arrives, and yet still remain concentrated enough to matter. This means Earth is both a narrow target and, in another sense, an exposed one. A coronal mass ejection moving broadly outward may miss the planet entirely, strike it directly, or glance across one side of its space environment. Even a partial encounter can produce significant effects if the magnetic structure and speed are favorable for strong interaction. Because Earth is small relative to the full width of space, forecast uncertainty often persists until the disturbance is much closer. Earth's orientation in space also matters. One half of the planet faces the Sun at any given time, receiving light, heat, and the earliest radiation effects from a flare. The other half faces away into darkness. This simple division shapes many later consequences, especially in the upper atmosphere and radio environment. But even before those details are considered, the planet's day and night sides establish that the encounter with solar activity is never perfectly uniform. Earth presents a rotating face to space. As it turns, different regions move into and out of exposure to changing conditions. The planet is therefore not a still object waiting passively. It is in constant motion within a larger moving system. The region around Earth is also occupied by human technology. Thousands of active satellites move in low orbit, medium orbit, geostationary orbit, and other paths. Space stations, navigation systems, weather platforms, communication satellites, and scientific spacecraft all share the near-Earth environment. Their presence does not alter the large-scale physics of an incoming solar disturbance, but it changes the practical meaning of the warning. Earth in open space is no longer only a natural body, It is a planet surrounded by instruments, machines, and infrastructure that extend human dependence into orbit. The next 72 hours are watched closely in part because the conditions near Earth affect far more than the planet itself. Even so, in this section the focus remains on Earth as a world placed within the solar flow, before attention narrows to the boundaries and layers that provide partial protection. Another important feature of Earth's place in space is that it moves through regions of differing magnetic connection to the Sun. The magnetic field carried outward by the solar wind does not connect uniformly everywhere. At some times, Earth's location relative to the spiral field makes it easier for energetic particles from a solar event to reach the planet's vicinity. At other times, connection is less direct. This is one reason why similar solar eruptions do not always produce identical near-Earth conditions. Earth is always present at roughly the same average distance from the Sun, but the detailed magnetic route between source and target changes. The planet's encounter with solar activity is therefore shaped by geometry as much as by distance. In open space, there is also no ordinary air to slow charge particles in the way the lower atmosphere slows motion at the surface. Plasma, radiation, and magnetic disturbances move through an environment that is extremely thin yet physically active. The solar wind itself is tenuous, but its particles carry momentum. Its magnetic field carries stress. When a disturbance approaches Earth, it does so across a medium that can compress, bend, and transmit pressure over enormous distances. Experts watch upstream spacecraft because those instruments act as early samplers of what Earth is about to meet. The warning grows clearer when the planet's immediate upstream space begins to change in measured ways. The phrase Earth in open space also means that the planet cannot rely on distance alone for safety. Earth is protected in important ways, but those protections are not part of emptiness. They come from the planet's own magnetic field and atmosphere, both of which must interact with what arrives from the Sun. Before focusing on those shields in detail, it is enough here to see Earth as a sphere exposed to the outer conditions of the solar system. It has mass, gravity, and an atmosphere. But from the vantage point of interplanetary space, it remains a small illuminated body immersed in a flowing magnetized medium. This simple image helps explain the calm seriousness of expert attention. Nothing unusual needs to happen at the ground for a warning to be scientifically justified. The planet's larger environment may already be shifting. The 72-hour interval often feels long in human routine. Yet in planetary space it is a brief passage. Earth moves millions of kilometers along its orbit in that time. The solar wind continues to stream outward. Disturbances launched from the Sun cross the gap and gradually approach the planet's location. Forecast centers update expected arrival windows because Earth is not waiting beneath a fixed sky. It is traveling through the very system that produces the disturbance. A shift of only several hours can change where the planet meets the most compressed or magnetically intense part of an incoming structure. Timing, position, and orientation all remain bound together. In this quiet outer region, Earth appears vulnerable not because it is weak, but because it is small within a vast plasma environment. Its blue atmosphere is thin. Its orbital path keeps it embedded in the Sun's influence at all times. Its day side and night side divide exposure. Its surrounding satellites multiply the practical significance of changing conditions. Its location in the magnetic spiral affects what reaches it first. Open space is therefore not a blank stage around the planet. It is the setting in which Earth receives solar energy, plasma, and magnetic change as ordinary facts of existence. Space experts watch this region carefully because it is where a solar event becomes a planetary concern in a direct spatial sense. The Sun has already released energy and matter. The solar wind has already provided the path. Now Earth stands within that path as a moving world, carrying atmosphere, oceans, life, and technology through a stream that never fully stops. In the next 72 hours, what matters first is simply this position. Earth is there, in open space, exposed to what the Sun sends outward. Around Earth, the first true shield against the solar wind is not the atmosphere but the magnetosphere, the region of space controlled mainly by the planet's magnetic field. In open space, Earth appears small and exposed. Here, that exposure meets structure. The magnetosphere is not a solid shell. It is a vast, invisible boundary system formed where the outward pressure of Earth's magnetic field balances the inward pressure of the solar wind. This region becomes the next focus because it is where approaching solar disturbances first press directly against the planet's protective field. When experts warn about the next 72 hours, much of their concern rests on what happens at this contact zone, where flowing plasma from the Sun meets Earth's magnetic defense. Earth's magnetic field arises largely from motion in the liquid outer core, where conductive material circulates and sustains a global magnetic pattern. Far from the planet, that field resembles a dipole in first approximation, somewhat like the field around a bar magnet, though the real structure is more complex and changes over time. On the side facing the Sun, the field is compressed by the solar wind. On the side facing away, it is stretched far out into space. This asymmetry defines the magnetosphere. It is shorter and more compact on the day side, longer and drawn out on the night side. The whole structure exists because the solar wind is always pressing and Earth's magnetic field is always resisting. The outermost dayside boundary is called the magnetopause. This is the surface where the solar wind and Earth's magnetic field come into direct balance. Beyond it lies the shocked solar wind and the interplanetary medium. Within it lies magnetic space more closely controlled by Earth. The magnetopause is not fixed in one place. When the solar wind is weak, it stands farther from Earth. When the solar wind becomes denser or faster, or when an incoming disturbance increases the pressure strongly, the boundary is pushed inward. During powerful events, this compression can become significant. Satellites that usually orbit within the protective region may find themselves nearer the boundary or even briefly outside it, depending on altitude and location. This is one reason forecasts of solar wind pressure matter as much as forecast of arrival time. Ahead of the magnetopause, on the Sun-facing side, lies another important region called the bow shock. A shock is a sharp transition where the fast solar wind slows, heats, and changes direction as it encounters the obstacle formed by Earth's magnetic field. The bow shock is similar in broad physical principle to the shock wave that forms ahead of a supersonic object moving through air, though here the medium is plasma and magnetic field rather than ordinary gas alone. The solar wind must reorganize itself before flowing around the magnetosphere, and the bow shock marks that first abrupt adjustment. Between the bow shock and the magnetopause lies the magnetosheath, a region of disturbed solar wind that has been compressed, heated, and redirected. This sheath is turbulent by comparison with the upstream solar wind, and it becomes especially important during strong solar events. When a coronal mass ejection or compressed solar wind stream reaches Earth, the first large-scale contact occurs across these boundaries. The bow shock responds to the enhanced flow. The magnetosheath grows more pressured and structured. The magnetopause moves inward. These changes can happen over tens of minutes to hours as the incoming solar plasma reorganizes the near-Earth space environment. Scientists watch them closely because they show how much of the disturbance is being transferred into the magnetosphere. Pressure alone is important, but magnetic orientation is equally important. If the magnetic field carried by the solar wind points in a direction opposite to Earth's field at the dayside boundary, reconnection becomes easier. In this context, reconnection means the incoming solar magnetic field and Earth's field link together and change their topology, allowing energy and plasma to enter more efficiently into Earth's space environment. This is one of the central processes of space weather near Earth. If the solar wind magnetic field points northward in a way more aligned with Earth's dayside field, the interaction may be less effective. Pressure may still compress the magnetosphere, but energy transfer can remain more limited. If the field points strongly southward, opposite to Earth's northward dayside field, coupling becomes much stronger. Then the solar wind is no longer merely pressing on the shield. It is opening pathways through it. This distinction helps explain why some arrivals produce modest geomagnetic activity, while others lead to stronger storms. The speed and density of the incoming solar plasma matter, but the magnetic direction within it often determines how much of that energy Earth's magnetic environment actually absorbs. The magnetosphere is therefore not a wall that simply blocks the sun. It is a dynamic interface. Under quiet solar wind conditions, it deflects most incoming plasma around the planet. Under disturbed conditions, it is compressed, distorted, and partially opened through magnetic connection. Plasma can enter, electric currents strengthen, magnetic energy begins to accumulate deeper in the system. In this section, however, the focus remains on the boundary itself and the first contact there. The larger reconfiguration of the nightside system belongs later, here. The key fact is that the dayside shield bends and responds, and that its response depends on the detailed properties of the solar wind. Spacecraft placed upstream of Earth, especially those near the point between Earth and Sun where gravitational and orbital conditions allow continuous monitoring, provide vital measurements of the solar wind just before it reaches the magnetosphere. These measurements include speed, density, temperature, and magnetic field direction. They give forecasters a short but crucial warning interval, often measured in tens of minutes, during the 72-hour period under close watch. These upstream readings become especially valuable because they turn a broad solar prediction into an immediate near-Earth diagnosis. Analysts can see whether the incoming flow is sharp or gradual, whether pressure is rising rapidly, and whether the magnetic field is turning into a more dangerous orientation for geomagnetic coupling. The boundaries themselves are never perfectly smooth. Waves ripple along them, instabilities form, local reconnection sites appear and vanish. The magnetosheath carries fluctuations from the shocked solar wind, and the magnetopause responds in a layered, changing way. Yet even through this complexity, the larger pattern remains readable. Higher dynamic pressure pushes inward, strong southward magnetic field enhances energy transfer, the bow shock strengthens, the sheath thickens in places. The magnetopause shifts. These are the quiet mechanical facts beneath the warning. They are not dramatic in appearance to human sight, because the structures are invisible without instruments, but they are central to everything that follows. For Earth's surface, nothing in this region is directly felt in a simple everyday sense. Skies may look unchanged, oceans remain calm under ordinary weather, streets continue under sunlight or darkness according to the hour. But high above, the first physical encounter between a solar disturbance and Earth's defense is underway. The magnetosphere is taking the impact, absorbing some of it, redirecting some of it, and in certain magnetic conditions allowing deeper entry of energy. This is why scientists speak carefully of boundaries rather than barriers. A boundary can move, bend, and connect. It can protect while also transmitting stress inward. In this outer protective region, pressure meets protection in a form that is entirely physical and measurable. The solar wind approaches as flowing plasma and magnetic field. Earth answers with its own magnetic envelope. Between them lie the bow shock, the magnetosheath, and the magnetopause, each changing as the incoming disturbance strengthens or relaxes. The warning about the next 72 hours becomes more immediate here because the event is no longer only approaching Earth. It is pressing on the very boundary that defines Earth's near space shield, testing how the planet's magnetic protection will respond. On the side of Earth turned away from the Sun, the magnetosphere does not end close behind the planet. It is drawn outward into a long magnetic extension called the magnetotail. This region forms because the solar wind flows past Earth and stretches the planet's magnetic field far into the night side of space. In the previous region, the day side boundary meets pressure and transfers energy inward when conditions allow. Here, that transferred energy is carried deeper into the stretched magnetic system behind Earth, where it can gather, reorganize, and later return in a more active form. Space experts watch this region closely during a 72-hour warning, because strong geomagnetic storms depend not only on dayside impact, but also on what the tail stores and releases. The magnetotail is not a simple single tube. It has structure. Its outer parts are called the tail lobes, regions where magnetic field lines are stretched in opposite directions on the northern and southern sides of the tail. Between these lobes lies a central plasma sheet, a hotter and denser region containing charged particles and electric currents. In the lobes, particle density is low and the magnetic field is relatively strong. In the plasma sheet, density is higher and the field is weaker. This arrangement matters because it allows the tail to act as a reservoir of magnetic energy. When solar wind energy is coupled efficiently into Earth's magnetosphere, especially during periods of strong southward interplanetary magnetic field, the tail becomes more stretched and more loaded with energy. This loading process is gradual on human timescales, often unfolding over many tens of minutes to several hours. As reconnection on the day side links Earth's field with the solar wind, magnetic flux is carried over the polar regions and into the tail. There it accumulates in the lobes, increasing magnetic stress. The tail stretches farther, and the central current sheet between the lobes can thin. Scientists often describe this state as one of growing tension. Though the underlying process is precise and measurable, energy from the solar wind is being stored in the magnetotail in magnetic form. The planet's night side field is not merely trailing behind like a passive wake. It is actively changing, building toward possible reconfiguration. This is why the magnetotail is so important in storm development. A geomagnetic storm is not only a matter of what presses against Earth from outside, it is also a matter of how Earth's own magnetic environment responds internally. The night side tail can reach a state where it becomes unstable. When that happens, magnetic reconnection may occur within the tail itself, often many tens of thousands of kilometers behind Earth. In that event, oppositely directed magnetic field lines in the stretched tail break and reconnect, releasing stored magnetic energy. Part of that energy drives plasma farther down the tail away from Earth. Another part sends energized plasma and reconfigured magnetic fields back toward Earth. This return flow is a central part of substorms and contributes to the broader development of geomagnetic activity. A substorm is a shorter and more localized disturbance within the magnetosphere, often associated with sudden brightening and expansion of auroral activity. A geomagnetic storm is larger in scale and longer in duration. The two are related but not identical. During strong solar forcing, repeated substorm activity can accompany the broader storm. In this region of the story, however, the focus remains on the magneto-tail as the place where energy accumulates and is episodically released. This helps explain why a solar event does not always produce its strongest effects immediately upon arrival at Earth. Sometimes there is an initial response at the dayside boundary, followed by further intensification as the tail continues to load and unload energy over time. The central plasma sheet plays a major role in this behavior. It is a region where particles move, heat, and carry current across the tail. During disturbed periods, it can become more active, with flows moving earthward and tailward as reconnection occurs. Bursts of fast plasma motion travel through this sheet, transporting both particles and magnetic structure. These flows are not smooth in a simple sense. They can be intermittent and patchy, yet taken together. They reveal that the magneto-tail is a working system, not a static extension. Magnetic energy stored in the stretched lobes is converted into motion, heat, and particle acceleration. This process changes the conditions throughout near-Earth space. One important feature of tail reconnection is timing. It does not begin merely because a solar disturbance has arrived. It depends on how much energy has already been transferred into the magnetosphere and on the evolving state of the tail current sheet. During prolonged intervals of southward magnetic field in the solar wind, the tail may continue to load for hours. Then, when reconnection begins, activity may intensify rapidly. This is one reason forecasts are updated repeatedly during a 72-hour warning window. A storm can strengthen in stages. Early pressure and magnetic coupling at the front boundary may be followed later by stronger internal magnetospheric release as the tail becomes fully engaged. The shape of the magnetotail also changes during disturbed conditions. It can become more stretched and thinner in its central sheet, then partially relax after reconnection. Earthward moving plasma flows can inject energetic particles closer to the planet. Tailward moving plasmoids, large structures of reconnected plasma and magnetic field, can be expelled down the tail away from Earth. These are signs that the tail is shedding some of the stress it had stored. Yet the process can repeat if solar wind driving continues. The tail may load again, reconnect again, and continue to contribute to storm time dynamics over many hours. Thus, the night-side system does not respond once and return immediately to quiet. It can cycle through repeated phases of accumulation and release. Scientists study the magnetotail with fleets of spacecraft when available, using coordinated measurements of fields, particles, and plasma flows. They also infer tail behavior from auroral observations, ground magnetometers, and global models of the magnetosphere. Because the tail stretches so far into space, no single instrument can capture all of it at once. Even so, the broad pattern is well established. Strong solar wind driving loads the tail. The lobes store magnetic energy. The current sheet thins. Reconnection can begin. Energy is then converted and redistributed through near-Earth space. Observations indicate these processes are central to geomagnetic disturbances, though the exact onset timing and local sequence remain difficult to predict in every event. In ordinary life at Earth's surface, the magnetotail is invisible and unknown to most people. It extends away from the dark side of the planet, far beyond the atmosphere and far beyond the range of ordinary sight. Yet in space weather, it is one of the most consequential regions. It determines whether incoming energy remains mostly at the boundary or penetrates deeper into the planetary magnetic system. It governs how stress builds after the initial encounter with the solar wind. It helps produce the night-side signatures that later become visible nearer Earth in auroral regions and measurable across the magnetic field of the planet. The warning about the next 72 hours therefore becomes more than a notice of arrival. It becomes a notice of development. The solar disturbance may already be pressing at the day side, but the tail behind Earth is now part of the evolving event. In its stretched lobes and active plasma sheet, magnetic energy accumulates quietly, then may be released with increasing intensity. The night-side magnetosphere holds this stored strain in a long, dark extension, and in that distant region storm growth takes shape. Within Earth's magnetic environment, closer to the planet than the long tail and yet still far above the atmosphere, charged particles can become trapped for long periods in regions known as the radiation belts. These belts form because Earth's magnetic field guides charged particles into spiraling paths around magnetic field lines, while also causing them to bounce between the northern and southern magnetic regions and drift around the planet. In this region of the story, attention narrows from the large-scale storage of magnetic energy in the magnetotail to the populations of energetic particles that circle Earth in invisible rings. During disturbed space weather, these belts can change in ways that matter greatly for spacecraft and for the broader near-Earth environment. Experts watch them carefully because they are not fixed structures. They respond to storms, and in strong events they can become more hazardous over timescales of hours to days. The radiation belts are often described in two main zones, though the real structure is more complex and can shift during active periods. The inner belt lies closer to Earth and is generally more stable. It contains many high-energy protons and some electrons. The outer belt lies farther out and is more variable, especially in its electron population. Between them there is often a region of lower particle intensity called the slot region, though this gap can fill or change during disturbances. These belts are not solid bands or visible rings. They are statistical regions where the number and energy of trapped particles become especially high. Their form depends on Earth's magnetic field, the sources of incoming particles, and the processes that accelerate, transport, and remove them. A charged particle trapped in Earth's magnetic field does not travel in a simple circle. It performs several motions at once. It spirals rapidly around a magnetic field line. It bounces between mirror points in the northern and southern hemispheres because the magnetic field grows stronger nearer Earth, reflecting the particle back and forth. At the same time, it drifts slowly around the planet due to gradients and curvature in the magnetic field. This combination of motions allows populations of particles to remain trapped over broad regions. The belts are therefore a product of magnetic geometry and particle dynamics together. They are one of the clearest examples of how Earth's magnetic field creates structure in near-Earth space. The particles in the belts come from several sources. Some are produced when cosmic rays interact with Earth's atmosphere and generate secondary particles, especially in the inner belt. Others are supplied more directly from the solar wind and from plasma populations already present in the magnetosphere. During geomagnetic storms, injections of particles from the magnetotail and changes in electric and magnetic fields can transport fresh material inward. Waves in the plasma can then accelerate electrons to very high energies. This is why storm conditions matter so much. A disturbed magnetosphere does not merely shift existing particles slightly. It can reshape the entire balance between source, acceleration, transport, and loss, leading to major changes in radiation belt intensity. The outer radiation belt is especially sensitive to these storm-time processes. After a strong solar wind disturbance, the number of energetic electrons in the outer belt may increase sharply, decrease sharply, or do both in sequence. Sometimes a storm strips away part of the outer belt by scattering particles into the atmosphere or outward into space. In other cases, wave-particle interactions accelerate electrons to what are often called relativistic energies, meaning speeds close to the speed of light. These highly energetic electrons are a serious concern for satellites because they can penetrate shielding, accumulate in materials, and trigger deep dielectric charging. Deep dielectric charging occurs when energetic electrons enter insulating materials inside a spacecraft, build up electric charge, and later discharge in ways that can damage electronics or disrupt operations. The inner belt is usually more stable, but it too can change under strong disturbance. Additional temporary zones of high-energy particles may appear between the main belts during major events, lasting for weeks or even longer in some cases. Observations indicate that the belts can reorganize quickly following strong solar activity. Yet the exact evolution depends on many factors, including the duration of southward interplanetary magnetic field, the speed and pressure of the solar wind, the occurrence of substorms, and the spectrum of plasma waves generated during the event. It remains uncertain in specific cases exactly how the electron population will evolve over the next several days, even when the solar driver is well measured. This uncertainty is one reason satellite operators remain cautious and continue updating risk assessments throughout a storm. Several types of plasma waves play an important role in the radiation belts. Chorus waves, which are naturally occurring electromagnetic emissions in near-Earth space, can accelerate electrons to higher energies under the right conditions. Other waves can scatter particles into the atmosphere, where they are lost from the belts. The balance between acceleration and loss is delicate. A storm may first remove particles from one region, then seed new lower energy particles, then accelerate those particles into a fresh belt enhancement. The belts therefore behave less like simple reservoirs and more like dynamic systems under constant competition between input and removal. During the 72-hour interval that experts are watching, this competition may unfold in multiple stages rather than in one single response. For satellites, the radiation belts are among the most operationally significant regions in near-Earth space. Spacecraft in medium orbit, highly elliptical orbit, and geostationary orbit may spend long periods within or near the outer belt. Instruments can suffer noise. Solar panels degrade slowly under cumulative exposure. Internal charging risk rises when energetic electron flux increases. Components may reset unexpectedly, and protective procedures may be required. Even spacecraft in low Earth orbit are not fully exempt, because some orbital paths pass through regions where the inner belt comes unusually close to Earth, such as the South Atlantic anomaly. In that region, the offset of Earth's magnetic field allows trapped radiation to dip nearer the surface, increasing exposure for satellites and, to a smaller degree, for aircraft at very high altitudes. Scientists monitor the belts with dedicated spacecraft, onboard dosimeters, particle detectors, and models that combine measurements from many missions. They track how electron and proton fluxes change with time, altitude, magnetic coordinates, and local time around Earth. These observations help operators decide when to delay sensitive operations, power down some systems, or alter spacecraft orientation, yet the belts remain difficult to predict in full detail. A major geomagnetic storm does not produce one simple radiation outcome. It produces a sequence of conditions, and the response of the belts depends on how long the driving continues and how internal wave activity develops. This region of the story remains invisible to ordinary sight, but it is densely important for modern technological life in orbit. Here, Earth's magnetic field does more than shield, it traps. The same magnetic structure that protects the atmosphere from direct solar wind erosion also creates regions where energetic particles can remain concentrated. Under quiet conditions, these belts are already significant. Under storm conditions, they can intensify and shift rapidly, increasing the hazard to machines that orbit within them. The warning about the next 72 hours, therefore, includes more than the arrival of a solar disturbance at Earth. It includes the possibility that Earth's own trapped particle environment will become more dangerous after that arrival. In the radiation belts, invisible rings under tension circle the planet as products of field, motion, and storm time change. They are not passive leftovers of earlier events. They are active populations that respond to incoming solar energy and to magnetospheric dynamics. As the larger geomagnetic disturbance develops, these belts can become rearranged, enhanced, depleted, or reshaped in ways that matter across much of near-Earth space. Their quiet persistence and sudden variability make them one of the central inner regions of the event now unfolding around Earth. Within and around the changing particle environment near Earth, human-made spacecraft continue to circle the planet in many different orbital paths. Some move through low Earth orbit only a few hundred kilometers above the atmosphere. Some travel through medium orbital regions used by navigation systems. Some remain near geostationary height, where they circle Earth once per day and appear fixed above one region of the surface. Others follow elongated paths that carry them through multiple parts of the magnetosphere. In this region of the story, attention turns from trapped particles themselves to the machines that must endure them. During disturbed space weather, satellites do not all face the same danger at the same time. Their risk depends on orbit, shielding, design, current activity, and the specific kind of disturbance moving through near-Earth space over the coming 72 hours. A satellite is both resilient and delicate. It is built to withstand vacuum, temperature extremes, radiation, and the long demands of orbital life. Yet it is also a compact arrangement of electronics, sensors, power systems, communication links, and moving parts that can be disrupted by the space environment. Some effects are gradual. Solar panels lose efficiency over time as radiation damages their materials. Surfaces age under ultraviolet exposure and charged particle bombardment. Other effects are sudden. A charged particle can strike a microelectronic component and cause a single event upset, which is a change of state in a memory element or logic circuit caused by one energetic particle. In many cases, the system recovers. In some cases, it resets, enters a safe mode, or requires ground intervention. During geomagnetic disturbances, one major concern is spacecraft charging. This occurs when different parts of a satellite accumulate electric charge from surrounding plasma or from penetrating energetic particles. Surface charging usually develops when lower energy particles build up on exterior materials. Deep charging occurs when more energetic electrons penetrate into internal insulating materials and later discharge. Either kind can create electrical discharges that interfere with electronics or sensors. The risk rises especially for satellites in geostationary orbit and other regions exposed to enhanced fluxes of energetic electrons from the outer radiation belt. Operators watch these conditions carefully because a discharge may mimic hardware failure, even when the underlying cause is environmental. Low Earth orbit satellites face a somewhat different set of dangers. They are more sheltered from the harshest regions of trapped radiation than spacecraft farther out, though not completely. Their most immediate storm time risk often comes from the upper atmosphere rather than from the radiation belts alone. When solar activity heats and expands the upper atmosphere, the density at low orbital altitudes can rise. This increase remains extremely thin by ordinary standards. But for a fast-moving spacecraft it matters. Drag increases, orbits decay more quickly, satellites lose altitude faster than expected. Predictions of orbital position become less accurate if atmospheric expansion is not updated promptly in models. For large satellite constellations and for debris tracking, this effect becomes operationally important during strong geomagnetic storms. The problem is not limited to active satellites. Defunct satellites and fragments of debris also respond to changing drag. Their altered motion can complicate conjunction assessment, which is the process of calculating the risk of close approaches or collisions in orbit. A geomagnetic storm may therefore affect the basic geometry of traffic in low Earth orbit. An active spacecraft trying to maintain a precise path must respond to a background environment that is itself shifting. Some missions can raise orbit or adjust their position. Others have limited fuel and must accept temporary uncertainty. This is one reason why storm warnings matter even when no satellite has yet reported a malfunction. The environment alone can make orbital operations more difficult. Communication and navigation satellites in higher orbits face additional vulnerabilities. Energetic particles can interfere with star trackers, which are optical instruments used to determine spacecraft orientation by observing stars. Sensors may produce noisy readings. Solar arrays may generate fluctuating output if the spacecraft enters unusual charging conditions, or if protective systems alter normal operating mode. Onboard computers may detect anomalies and switch to safer, more limited configurations. During storm intervals, some operators postpone software uploads, delicate maneuvers, or instrument calibrations because the environment is less predictable. A satellite can remain physically intact and still lose part of its usefulness for hours or days if its measurements become less reliable or if protective procedures reduce functionality. Spacecraft also depend on communication links that pass through Earth's upper atmosphere and ionosphere. Disturbance in those regions can degrade signal quality, increase timing error, or interrupt high-frequency radio paths. Although those atmospheric regions belong more properly to later sections, the effect is already meaningful here because the satellite itself may be working normally, while the path between spacecraft and ground becomes less stable. This distinction matters in operations. A lost signal does not always mean the spacecraft has failed. It may mean that the surrounding space environment has become less favorable for transmission or tracking. Forecasters and mission teams therefore combine space weather data with spacecraft telemetry to determine whether a problem is internal, external, or both. Some satellites are designed specifically to observe the sun, the solar wind, or the magnetosphere, and these missions become especially valuable during a storm. They provide the measurements that allow other operators to respond. Yet even they are not immune to the environment they monitor. Instruments may saturate under intense particle flux. Detectors may require correction for background contamination. Temporary data gaps can occur if systems enter protective states. This creates an important practical truth. The more active the space environment becomes, the more essential measurements are, and at the same time the harder some of those measurements may be to maintain cleanly. Human dependence on satellites broadens the meaning of every such disturbance. Weather forecasts, navigation timing, financial networks, environmental monitoring, communications, television distribution, disaster response, shipping, aviation, agriculture, and military systems all rely to some extent on spacecraft. A space weather event does not need to destroy satellites to matter. It only needs to degrade their performance, reduce confidence in their outputs, or force operators into conservative modes. Many storms pass with limited visible consequence because engineering margins, operational caution, and forecasting all work together successfully. Even so, the risk is real and measured. The warning about the next 72 hours is partly a warning the orbital systems may face conditions outside their most comfortable range. Different spacecraft respond differently because design choices matter: shielding thickness, component quality, grounding strategy, fault tolerance, and software resilience all influence storm survival. A hardened satellite may pass through a period of elevated radiation with no obvious trouble. A more vulnerable one may experience repeated anomalies. The same environmental event can therefore produce a scattered pattern of effects across fleets. This can make the early hours of a storm difficult to interpret. One operator reports no issue, another reports sensor noise, a third sees charging indicators rise. Only after comparing many systems with environmental measurements does a broader picture emerge. This region of the story is therefore one of moving machines passing through a moving hazard. The satellites themselves keep their scheduled orbits, but the space through which they travel no longer behaves as a quiet background. Radiation intensifies in some regions. Charging risk rises. Drag changes in low orbit. Signals become less certain. Precise predictions require constant revision. All of this unfolds above the weather and above the ordinary rhythms of life at the ground. Yet it reaches deep into modern society because so much now depends on stable orbital service. In the next 72 hours, spacecraft in near-Earth orbit will continue circling through these changing conditions. Some will cross the outer radiation belt again and again. Some will feel the subtle thickening of the upper atmosphere below. Some will remain outward-facing sentinels, measuring the environment for everyone else. Their vulnerability is not dramatic in appearance, but it is scientifically clear. Machines built for space must still adapt when space itself grows more unsettled. Beyond the densest protection of Earth's atmosphere and outside the safer depths of the magnetic shield, human beings in space become part of the event in a more direct biological sense. In this region of the story, attention turns from machines to living bodies. The concern is not only whether spacecraft systems continue to function, but whether crews are exposed to rising radiation over short intervals of hours to days. Space experts watch this question with special care because radiation in space does not behave like an ordinary hazard at the surface. It cannot be seen or felt directly as it passes through tissue. Its effects depend on particle type, energy, shielding, duration, and location. During the next 72 hours, that combination becomes especially important for astronauts who are not deeply sheltered by Earth's atmosphere. At Earth's surface, the atmosphere provides strong protection against most high-energy particles from space. It absorbs and scatters them long before they reach sea level in significant numbers. Earth's magnetic field adds another layer of protection by deflecting many charged particles away from the lower atmosphere altogether. In orbit, and especially beyond low Earth orbit, these protections are reduced. A spacecraft hull can block part of the radiation environment, but no practical vehicle wall creates the kind of shielding provided by the full atmosphere. This is why human exposure in space is always managed through a combination of mission timing, orbit selection, spacecraft design, operational procedures, and continuous monitoring of solar activity. Radiation in space comes from more than one source. Even in quiet periods, astronauts are exposed to galactic cosmic rays, which are high-energy particles arriving from beyond the solar system. These are a persistent background. They are difficult to block completely, because the most energetic among them can penetrate substantial shielding. On top of this steady background, solar activity can add solar energetic particles, especially protons accelerated during flares and shock waves driven by fast coronal mass ejections. It is these solar particle events that matter most over short spans such as 72 hours. They can increase radiation levels quickly and substantially, especially for astronauts in deep space or in weakly shielded locations. A solar energetic particle event does not expose all crews equally. Location is decisive. Astronauts in low Earth orbit remain within a large portion of Earth's magnetic protection, although that protection is not uniform everywhere. The magnetic field guides many incoming particles away, especially at lower magnetic latitudes. Exposure can still rise in polar orbital regions and during major events, but low Earth orbit generally offers much more protection than cislunar space, the region around the Moon, or interplanetary travel. Crews on a lunar mission or on a future Mars voyage would have far less natural shielding available. In those regions, the spacecraft itself becomes the main protective barrier, and the quality of its shielding becomes a central operational concern. Shielding is a complicated matter. A thicker wall usually reduces exposure, but the material and particle energy both matter. High-energy protons can pass through thinner layers and deposit energy inside the body. Very energetic heavy particles can create secondary radiation when they strike shielding material, producing cascades of additional particles. For this reason, radiation protection in spacecraft is not just a matter of building the thickest possible shell. It involves careful material choice, structural design, and sometimes the creation of a more protected internal shelter area where crew members can remain during the peak of a solar particle event. Such a shelter is often located where supplies, water, equipment, and existing structure combine to create greater shielding than the rest of the cabin. Biologically, radiation matters because it can damage cells and genetic material. Over short timescales, a high enough dose can lead to acute radiation effects, including nausea, fatigue, and changes in blood cell counts. At much lower doses, immediate symptoms may not appear, but cumulative risk to long-term health still increases. Cancer risk is one of the major long-term concerns in space radiation protection during the 72-hour interval under discussion. However, the main issue is usually the possibility of a rapid increase in dose from a solar energetic particle event. Mission teams therefore track dose rate, which is the amount of radiation delivered over a given time, as well as the accumulated total dose. A brief intense event may pose a greater short-term operational concern than a longer period of moderate background exposure. The timing of crew exposure also depends on warning and response. Radiation from a solar flare reaches Earth quickly, but the most operationally significant proton flux may rise over tens of minutes to hours, depending on the event and the magnetic connection to Earth, or to the crew's location in space. This limited interval can still be important. If monitoring systems detect a strong event early enough, astronauts may move into a better shielded area of their spacecraft and postpone any activity that would increase exposure. Spacewalks are of particular concern because a spacesuit provides far less shielding than a spacecraft cabin. For this reason, planned extravehicular activity may be delayed when solar activity becomes more threatening. A crew outside the main hull during a fast-rising particle event would have very little protection beyond warning time and rapid return capability. For crews aboard orbiting stations, the risk over 72 hours is usually managed with established procedures. Flight control teams monitor solar conditions continuously. Dosimeters inside the vehicle measure the radiation environment. If particle levels rise, crew members can modify schedules, remain in more shielded modules, and avoid unnecessary exposure in less protected locations. These measures do not remove the hazard, but they reduce it. Observations indicate that low Earth orbit missions are generally far safer from acute solar radiation than deep space missions, though not entirely free from risk. The exact level of concern in any event depends on the strength of the particle storm, the orbit's geometry relative to Earth's magnetic field, and the station's shielding distribution. The situation becomes more serious in missions beyond low Earth orbit. Near the Moon, or on interplanetary routes, there is no broad geomagnetic shield to deflect incoming charged particles. A strong solar particle event in those regions can become one of the most serious short-term hazards faced by astronauts. For this reason, mission planners treat solar forecasting as part of life support in a broad sense. Crew safety depends not only on oxygen, water, and temperature control, but also on the ability to detect solar changes, assess probable particle intensity, and protect the crew within the vehicle. Yet uncertainty remains. Forecasting particle intensity from the earlier solar observations is still imperfect. Scientists can identify elevated risk, but they cannot always specify exactly how intense the proton event will become at a given location. This uncertainty is why caution tends to increase quickly when solar conditions suggest a growing chance of strong particle acceleration. Radiation risk is also shaped by human physiology and mission duration. A dose that would be acceptable over a short mission may be less acceptable when added to earlier exposure from previous flights or from a long mission already underway. Space agencies therefore manage exposure through cumulative career limits as well as event-specific thresholds. In a 72-hour warning window, these larger planning rules remain in the background, but they help explain why even modest increases in radiation receive close attention. Each event adds to a broader picture of total exposure over time. In this inner human region of the story, the meaning of the warning becomes deeply practical. Space is no longer only a domain of fields, particles, and machines. It is a place where human bodies may be present, relying on thin layers of engineered shelter against an invisible environment that can change quickly when the sun becomes active. Experts do not speak dramatically because the science is already serious enough. A strong solar particle event is measurable, biological, and operational all at once. Over the next 72 hours, crews beyond deep natural protection must depend on monitoring, shielding, and disciplined response as the space around them continues to change. Below the region of orbiting spacecraft and below the trapped radiation belts, Earth's upper atmosphere begins to respond directly to the changing flow of solar energy and geomagnetic activity. This region is still far above ordinary weather, yet it is no longer open space in the same sense as the magnetosphere. Here the air is extraordinarily thin, but it is air nonetheless, composed of atoms and molecules that can be heated, ionized, expanded, and chemically altered by what arrives from the sun and from near-Earth space. In this part of the story, attention turns to the upper atmosphere as a physical layer that reacts to the storm, grows less settled, and begins to transmit its changes downward into the practical conditions of satellites, radio paths, and orbital motion. The upper atmosphere includes the thermosphere, where temperature rises with height because solar radiation is absorbed by sparse gases. The word temperature here needs care. In such a thin region, individual particles can carry high energy, so the measured temperature may become very high, yet the total heat content remains low because there are so few particles. A human body would not feel this region as it feels warm air at the surface. Even so, the increase in particle energy matters greatly for atmospheric structure. When X-rays, extreme ultraviolet light, and energetic particles increase during solar activity, They deposit additional energy into the upper atmosphere. Atoms and molecules move faster. The gas expands upward and outward. Density rises at altitudes where satellites travel. This is one of the clearest and most immediate atmospheric responses during disturbed space weather. The thermosphere is made largely of oxygen atoms, nitrogen molecules, and, at greater heights, lighter species such as helium and hydrogen. Under quiet conditions, the distribution of these gases changes gradually with height and with the daily cycle of sunlight. Solar heating is strongest on the day side of Earth and weaker on the night side, so temperature and density are already uneven even before a storm begins. During a solar event, that unevenness becomes more pronounced and more dynamic. The sunlit atmosphere absorbs enhanced radiation quickly. Then, as geomagnetic activity develops, energy also enters from high latitudes where charged particles and electric currents interact with the upper atmosphere. The result is not a simple uniform swelling, but a changing global response with local peaks, delayed spreading, and strong differences between latitude, local time, and altitude. This expansion of the upper atmosphere has practical importance because low-orbiting satellites move through it at very high speed. Even a small increase in density can produce a noticeable increase in drag. Drag is the resisting force that acts opposite the motion of an object moving through a fluid, and the upper atmosphere, though extremely thin, is still enough of a fluid to matter over repeated orbits. During strong geomagnetic storms, the thermosphere can expand enough that satellites encounter denser air than expected for their altitude. Orbits decay faster, position forecasts become less accurate unless models are updated rapidly. Space debris tracking also becomes more difficult because many objects respond differently depending on area, mass, and shape. This atmospheric response therefore links solar activity directly to orbital uncertainty. Heating is not the only change. The chemistry of the upper atmosphere also shifts. Enhanced radiation and particle precipitation alter the balance of ionized and neutral species. Molecules can be broken apart, new reactive forms can appear. In the lower part of the upper atmosphere, energetic particles can produce nitrogen oxides and hydrogen oxides, which may influence ozone chemistry under certain conditions, in the thermosphere and related regions. The main operational concern is less about ozone and more about how composition changes affect cooling, density, and coupling with the ionized layers above and within it. For example, nitric oxide can become an important cooling agent because it radiates energy away in infrared wavelengths. Thus, the atmosphere does not only heat and expand, it also develops pathways by which it can later shed part of that added energy. The upper atmosphere is tightly coupled to the ionosphere, the region where enough atoms and molecules are ionized that free electrons become a major part of the environment. Although the ionosphere will receive closer attention in the next section, its connection to the neutral upper atmosphere is already important here. When ionization increases, electrical conductivity changes. Electric fields and currents intensify in some regions. Ions and neutrals collide, transferring momentum and heat. Winds in the neutral atmosphere can alter the distribution of ionized plasma, and changes in plasma can feed back on the neutral flow. This means the upper atmosphere's storm response is not just passive heating from above. It is a coupled dynamical system in which radiation, charged particles, chemistry, winds, and currents all interact. At high latitudes, where geomagnetic field lines guide energetic particles downward more readily, the storm response can become especially strong. Particles entering the atmosphere there deposit energy through collisions, exciting atoms and molecules, ionizing the gas, and heating the surrounding region. Strong auroral activity is one visible sign of this energy input, but even without considering the light itself, the underlying heating is substantial. The atmosphere can rise locally. Horizontal winds can strengthen, and pressure gradients can drive motion across large distances. In this way, the upper atmosphere becomes more mobile. It is not simply inflated, it is stirred. Winds can carry the effects of heating from one region toward another, redistributing mass and energy over many hours. During a 72-hour period of sustained solar and geomagnetic activity, the upper atmosphere may not respond only once. It may be heated by the first radiation increase, then further disturbed by the arrival of a coronal mass ejection, then kept active by continued southward magnetic driving, substorms, and recurrent energy input at high latitudes. Density may rise, partially relax, and rise again. Forecasting this sequence is difficult because the atmosphere has memory. Its present state depends not only on the current solar wind conditions, but also on the heating it experienced earlier. This means that models must constantly be corrected with observations from satellites, accelerometers, drag measurements, and ground-based monitoring. A forecast based on quiet background assumptions can quickly become outdated when the atmosphere begins to expand more than expected. Scientists describe part of this process as thermospheric upwelling, meaning that heated air at high latitudes rises and changes the local composition and density structure. This upwelling can spread its influence through global circulation patterns. The response is therefore planetary in scale even if the strongest energy input begins in limited regions. What starts as enhanced radiation from the Sun and magnetospheric coupling at the poles becomes a broad change in the structure of the upper atmosphere around the world. The day-night contrast shifts, the density profile changes, the behavior of orbiting objects becomes less predictable. Communication paths that rely on stable upper atmospheric conditions begin to face new uncertainty. For people at the ground, all of this remains hidden. Clouds, wind, and rain in the lower atmosphere may continue according to ordinary weather patterns, with no sign of the heated thin air hundreds of kilometers overhead. Yet for scientific understanding, this region is crucial because it marks the point where space weather enters the atmosphere in a direct physical way. The planet's upper air is no longer just a distant boundary. It is now part of the event, absorbing energy, changing shape, and influencing systems that depend on predictable orbital and radio conditions. In the next 72 hours, experts therefore watch the upper atmosphere not as a background layer, but as an active participant in the storm. It heats under enhanced solar radiation. It expands as particle energy increases. Its composition shifts. Its winds strengthen in places. Its density changes alter the motion of satellites and debris. This high air, almost empty by ordinary standards, becomes a sensitive indicator of how deeply the solar disturbance is penetrating into Earth's environment. The warning that begins at the Sun now takes form in the thin atmospheric shell above the planet, where added energy turns a quiet region into a moving one. Within the changing upper atmosphere, there is a region where free electrons and ions become numerous enough to shape the passage of radio waves and to produce some of the most visible signs of geomagnetic activity. This is the ionosphere and the auroral zone, the part of near-Earth environment where incoming solar energy, magnetospheric currents, and atmospheric matter meet in a charged and responsive layer. In this region of the story, attention moves inward from the broad heating and expansion of the upper atmosphere to the specific ways in which charged layers and polar light begin to reveal the storm. Here the warning becomes visible in the sky at high latitudes and measurable in the failure or distortion of signals that normally pass quietly through the upper air. The ionosphere is not a separate atmosphere in the ordinary sense. It is a region extending through parts of the upper atmosphere where solar radiation and energetic particles remove electrons from atoms and molecules, creating a mixture of ions and free electrons. These charged particles affect how radio waves move. Some frequencies are reflected, some are refracted, some pass through with delay, and some are absorbed more strongly under disturbed conditions. The ionosphere is usually described in layers that vary with height, local time, season, and solar activity. On the day side of Earth, sunlight maintains strong ionization. On the night side, some layers weaken markedly because the source of ionizing radiation is absent. Even in quiet times, the ionosphere changes from hour to hour. During a solar event, those ordinary variations can become much larger and less predictable. The first response in this region may begin within minutes of a major solar flare. Enhanced X-rays and extreme ultraviolet radiation reach Earth rapidly and increase ionization on the sunlit side. In the lower ionosphere, especially in the D region, this can greatly increase radio absorption. High-frequency radio signals that would normally reflect or propagate over long distances may weaken or disappear across the day side. This effect is often called a radio blackout. Though it is rarely uniform in a simple sense, its strength depends on flare intensity, solar zenith angle, radio frequency, and path geometry. For forecasters, the importance of this response lies in its speed. The ionosphere can change almost at once under enhanced radiation, long before the slower solar plasma cloud arrives. As the broader geomagnetic disturbance develops, the ionosphere becomes more unsettled in additional ways. Electric fields from the magnetosphere map down along magnetic field lines into the high-latitude ionosphere. Particle precipitation increases in the auroral zones. Currents intensify, plasma drifts change direction and speed, density structures form and break apart. Some regions become more strongly ionized, while others lose plasma through transport or recombination. The result is not merely a stronger ionosphere, but a more irregular one. This irregularity matters because many modern systems depend on stable radio propagation and accurate timing through the upper atmosphere. When the ionosphere becomes patchy and dynamic, the path of a signal becomes harder to predict. One of the clearest visible expressions of this process is the aurora. In the northern hemisphere it is often called the aurora borealis, and in the southern hemisphere the aurora australis. The light appears when energetic particles guided by Earth's magnetic field enter the upper atmosphere and collide with oxygen and nitrogen. These collisions excite the atoms and molecules, raising them into higher energy states. When they return to lower states, they emit light. Green is common from oxygen at certain heights. Red may appear from oxygen higher up. Nitrogen can contribute blue or purple tones. The exact color and shape depend on altitude, particle energy, atmospheric composition, and the changing geometry of magnetic field-aligned currents. During quiet conditions, the auroral oval stays closer to the poles. During strong storms, it can expand toward lower latitudes. Although auroral light is often described in poetic terms, its scientific meaning is exact. It is evidence of energy entering the atmosphere from near-Earth space. Curtains, arcs, rays, and diffuse glows all reflect particle precipitation and the magnetic structure guiding it. Rapid brightening can indicate a substorm onset. Broad expansion can show that the magnetosphere is releasing stored tail energy into the near-Earth system. Even a steady auroral band marks a zone where the upper atmosphere and magnetosphere are strongly coupled. Thus, the visible sky at high latitude becomes a direct display of processes that began with solar activity and developed through the magnetosphere. In the present section, however, the aurora is not treated as spectacle. It is treated as a luminous signature of energy transfer, ionization, and atmospheric excitation. Signal disruption in the ionosphere takes several forms. High-frequency radio communication can fade because of increased absorption, or because the reflecting layers shift in height and density. This matters especially for aviation routes over polar regions, maritime communication, amateur radio, and some emergency systems. Satellite navigation signals, such as those used for positioning and timing, can also be affected. These signals pass through the ionosphere on their way from orbit to the ground. If the electron density along the path changes unexpectedly, the signal is delayed. Dual-frequency receivers can correct for much of this delay, but strong irregularities still reduce accuracy. More importantly, small-scale structures in the ionosphere can cause scintillation, a rapid fluctuation in signal amplitude and phase caused by irregular plasma density under strong scintillation. Receivers may struggle to maintain lock on the signal. These effects are often strongest near the equatorial and high-latitude ionosphere, though the detailed pattern varies with local time and storm phase. At high latitudes, auroral particle precipitation and electric fields produce intense variability. At lower latitudes, storm-enhanced plasma structures and post-sunset instabilities can create additional signal problems. In this way, a geomagnetic storm can disturb radio and navigation systems across widely separated regions for different reasons. Experts therefore track total electron content, radar backscatter, ionosonde measurements, satellite signal quality, and auroral indices to build a picture of ionospheric behavior as the event unfolds. The ionosphere also feeds back into other systems. Changes in ionospheric conductivity alter the strength and path of currents flowing between the magnetosphere and atmosphere. These currents contribute to magnetic fluctuations measured on the ground. Heating in the auroral ionosphere can drive neutral winds and atmospheric upwelling. Disturbance in radio communication can affect aircraft routing decisions, especially on polar routes where alternative frequencies may be limited. Thus, the ionosphere is not only a receiver of space weather effects, it is an active layer that helps shape how those effects spread through technology and geophysical measurement. Forecasting ionospheric response remains difficult because the system is highly variable even before a storm begins. Background density depends on season, solar cycle phase, and time of day. Storm time changes depend on flare radiation, solar wind pressure, magnetic orientation, auroral activity, thermospheric winds, and chemical loss rates. Observations indicate general patterns, such as increased dayside absorption during strong flares and enhanced high-latitude irregularity during geomagnetic storms. Yet it remains uncertain in specific cases exactly which communication links will fail, how severe navigation degradation will become, or how long local disturbances will persist after the main solar driver weakens. This uncertainty is why operational centers issue frequent updates rather than one single forecast. In this charged atmospheric region, light forms as signal struggle. The aurora reveals where energetic particles enter the upper atmosphere and transfer energy into visible emission. The ionosphere records the same disturbance in a less visible but equally important way, through shifting electron density, changing conductivity, absorption, delay, and scintillation. Over the next 72 hours, these layers may continue to brighten, thicken, thin, and fragment under the influence of solar radiation and magnetospheric forcing. What had been a mostly transparent upper medium for radio and navigation now becomes irregular and active, showing in both luminous sky and disturbed signal paths that the solar event has reached deeply into Earth's atmospheric shell. At Earth's surface, the solar disturbance is no longer a matter of distant light, invisible plasma, or orbital risk alone. In this region of the story, attention settles on the ground, where changing magnetic fields in near-Earth space can induce electric currents in long-conducting systems. This is the point at which a space weather event reaches directly into technological networks built across continents. The physical principle is simple in outline. When the magnetic field over a region changes with time, electric fields can be generated in the ground and in long conductors. Those electric fields drive currents through systems that were not designed to carry them in that way. During quiet times, these induced currents are weak. During strong geomagnetic disturbances, they can become operationally significant. This is why experts watching the next 72 hours pay close attention not only to the sky and to orbit, but also to power grids, pipelines, cables, and the magnetic behavior of the ground itself. Earth's magnetic field is normally present everywhere at the surface, though its strength and direction vary with location. During a geomagnetic storm, that field begins to fluctuate more rapidly and more strongly as currents intensify in the magnetosphere and ionosphere above. The most important surface effect comes not from the absolute value of the magnetic field, but from how quickly it changes. A changing magnetic field produces an electric field. Where the ground is conductive and where long-engineered conductors are present, that electric field can drive what are called geomagnetically induced currents. These are not currents generated by a power plant or by ordinary system operation. They are currents imposed from outside, entering a technological network because the geophysical environment has changed. Power transmission systems are especially vulnerable because they consist of long lines connected across wide areas and grounded through transformers. A transformer is a device that changes electrical voltage from one level to another through magnetic induction. It is designed for alternating current at a known frequency and for expected operating conditions. Geomagnetically induced currents, however, are effectively very low frequency or near direct currents from the perspective of the power system. When they enter a transformer, they can push its magnetic core towards saturation during part of the cycle. This process is called half-cycle saturation. When it occurs, the transformer operates less efficiently, draws more reactive power, heats unevenly, and can produce harmonics, which are unwanted electrical distortions at multiples of the normal operating frequency. Protective systems may trip, voltage regulation may degrade. In severe cases, physical damage can accumulate. Not every geomagnetic storm produces a major power problem. The outcome depends on many factors. The intensity and speed of magnetic field variation matter. Ground conductivity matters because the induced electric field depends partly on the structure of the subsurface. Regions with resistive bedrock overlain by more conductive layers can experience especially strong induced fields. The design of the grid also matters. Long transmission lines, transformer grounding practices, network topology, and real-time operating margins all influence vulnerability. A well-prepared grid may absorb a period of elevated induced current with limited visible consequence. A more stressed or less favorably configured system may experience alarms, equipment strain, voltage instability, or localized outages. This is why expert warnings are careful rather than absolute. Strong geomagnetic activity increases risk, but the exact ground outcome remains system-dependent. High-latitude regions tend to face greater exposure because geomagnetic disturbances and auroral electrojets are strongest there. An electrojet is a concentrated current flowing through the high-latitude ionosphere. When these overhead currents intensify and shift, magnetic variations at the ground can become large, yet lower latitude systems are not entirely exempt. During major storms, the disturbed region can spread equatorward, and broad-scale magnetic change can affect wide areas. The magnetic storm does not need to place an aurora overhead for induced currents to become relevant in a power network. What matters is the pattern of magnetic variation over the region and the electrical properties of the ground and grid beneath it. Pipelines also respond to geomagnetic disturbances. Long metal pipelines normally use corrosion protection systems that maintain a controlled electrical condition along the pipe. Geomagnetically induced electric fields can interfere with these systems by altering pipe-to-soil potential. This can complicate corrosion monitoring, and over-repeated exposure may increase long-term integrity concerns. Submarine cables and land communication lines may likewise experience induced voltages, though the practical consequences depend on system type and protection design. Railway signalling and other grounded infrastructure can also be affected under some conditions. The common factor is length. The longer the conductor and the wider the geographic span, the more opportunity there is for induced electric fields to produce unwanted currents or voltages. Ground conductivity is an important and often overlooked part of the story. The earth beneath a power grid is not electrically uniform. Some rock types conduct poorly. Sediments, groundwater content, coastal boundaries, and deep geological structure all influence how induced electric fields develop at the surface. Coastal regions can experience complex responses because the conductivity contrast between land and sea affects current flow. Therefore, two places under the same overhead magnetic disturbance may not experience the same ground electric field. Power engineers and geophysicists study these regional differences carefully in order to build hazard maps and improve real-time response. The storm in space is global in origin, but the induced current risk at the ground is strongly local in character. Monitoring these ground effects involves both geophysical and engineering measurements. Magnetometers record rapid changes in Earth's magnetic field at stations across the surface. Grid operators monitor transformer neutral currents, voltage stability, reactive power demand, and protective device behavior. Space weather centers compare upstream solar wind conditions with geomagnetic indices and local magnetic measurements to estimate where risk may be greatest. If the storm strengthens, operators may reduce loading on vulnerable parts of the network, postpone maintenance, bring reserve capacity online, or alter system configuration to improve resilience. These actions do not stop the induced electric fields, but they can reduce the chance that equipment stress becomes a broader grid problem. Historical events show why this attention is justified. Large geomagnetic storms have previously caused transformer damage, tripping events, and regional blackouts under unfavorable conditions. Observations indicate that the combination of strong magnetic variation, susceptible grid design, and local geology can produce serious consequences, though such outcomes remain infrequent. Modern grids are often more aware of this risk than in earlier decades, and forecasting has improved. Even so, the basic physics has not changed. Rapid geomagnetic variation above the surface can drive unwanted current below it and through infrastructure built for another purpose. For ordinary life on the ground, this region often remains unnoticed unless power quality changes. Communications degrade, or news reports draw attention to auroras and space weather alerts. Streets, buildings, and landscapes may look completely normal, while electrical systems quietly enter a more strained operating state. A transformer does not display the sky. A power network does not announce that the magnetosphere is disturbed. Yet beneath the calm appearance of the surface, long conductors may already be responding to the shifting field overhead. The solar event has now moved through every larger outer region and reached the practical foundations of technological society. In this inner surface region, distant storms reach the ground through the precise link between magnetic change and induced current. Power lines, transformers, pipelines, and other extended systems become part of the event not because the sun touches them directly, but because Earth's magnetic environment above them is changing in time. Over the next 72 hours, experts will watch ground magnetometers, transformer behavior, and regional electrical conditions with the same steady care used earlier for solar images and spacecraft data. The chain is now complete enough to show how a disturbance born in the sun's magnetic atmosphere can travel all the way to the surface and enter the circuits of the modern world. Over the course of 72 hours, the event is no longer understood as a single burst or a single impact. It becomes a measured interval in which many linked processes unfold at different speeds, in different regions, and with different levels of certainty. In this final section of the main script, attention does not return outward. It remains inward, within the human framework of observation, forecasting, and response that surrounds the event as it develops. The sun has already been watched. Space between sun and Earth has already been crossed. Earth's magnetic environment, upper atmosphere, ionosphere, spacecraft, and ground systems have already entered the chain. What remains here is the 3-day period itself. As experts compare forecast with measurements, revise expectations, and separate what is clearly happening from what still cannot be known in full detail. The first hours of such a period often carry the clearest contrast between speed and uncertainty. Radiation from a flare arrives quickly and can be measured almost at once. Solar images confirm the location of the source region. X-ray monitors show the rise and peak of the flare. Early particle monitors may begin to register increased counts. At the same time, forecasters still face open questions. How fast is the associated coronal mass ejection truly moving once projection effects are corrected? How wide is it in 3-dimensional space? Is Earth in the central path or only near the flank? Does the event travel alone? Or is it moving through a solar wind already altered by earlier eruptions or fast streams? The first data arrive quickly, but the fuller meaning of those data emerges more slowly. As the first day continues, the event becomes more constrained by measurement. Coronagraph images show whether the eruption expands as a halo or partial halo. Model runs estimate travel time to Earth based on speed, width, and drag through the solar wind. Solar wind forecasters compare current interplanetary conditions with the new ejection. Radiation effects on the dayside ionosphere may already be seen in high-frequency radio absorption and increased lower ionosphere ionization. If energetic particles are well connected to Earth's region of space, rising proton flux may lead to alerts for aviation, spacecraft operators, and crewed missions. Yet even during this early interval, the most consequential magnetic question may remain open. The internal magnetic orientation of the arriving structure is one of the hardest properties to know in advance, and it often determines whether the geomagnetic response will be limited or strong. This uncertainty is central to responsible forecasting. A fast arrival does not always produce the strongest magnetic storm. A slower structure with a long interval of southward magnetic field can sometimes drive a more sustained response than a faster one with less favorable orientation. Experts therefore avoid claiming more than the evidence supports. They issue probabilities, expected arrival windows, and likely ranges of disturbance. They distinguish between solar event strength and Earth impact severity. This caution is not hesitation. It is the ordinary discipline of a field in which some of the most important variables cannot be observed directly until the structure is much closer to Earth. By the second day, the event often becomes more immediate. Upstream spacecraft near the Sun-Earth line begin to provide direct measurements of the approaching solar wind structure before it reaches Earth's magnetosphere. A shock may arrive first, marked by a sudden increase in speed, density, temperature, and magnetic field strength. Dynamic pressure rises, the magnetosphere compresses, geomagnetic indices begin to respond. A storm's sudden commencement may be seen in ground magnetometer records as the global field shifts rapidly. This is the moment when many remaining uncertainties begin to narrow. The arrival is no longer modelled only from afar. It is being sampled directly in the solar wind just upstream of Earth. Still, the most important part may yet be unfolding. Behind the shock and sheath lies the body of the coronal mass ejection, or magnetic cloud, if such a structure is present. The sheath region ahead of it can already drive geomagnetic activity because it is turbulent and magnetically variable. Then, if the main cloud contains a strong southward field, storm conditions may intensify further and last longer. If the field turns northward instead, the storm may weaken more quickly than early warnings had feared. Thus, the 72-hour interval is often a moving sequence of reassessment. Experts do not merely wait for a storm to happen. They watch how each arriving region compares with prior forecasts and update the practical meaning of the event in near real time. As the event continues, different communities read the measurements through their own operational needs. Satellite operators watch particle flux, charging risk, drag changes, and anomalies in telemetry. Power grid operators watch ground magnetic variation, transformer behavior, and reactive power conditions. Aviation planners review polar communication reliability and radiation routes. Scientific teams monitor magnetospheric loading, auroral expansion, ionospheric irregularity, and thermospheric density. The underlying event is one connected physical chain, but its consequences are experienced as multiple specialized concerns. This is why space weather centers coordinate many streams of data at once. The warning about the next 72 hours is not one message for one audience. It is a layered assessment translated into different forms of action. The second and third days also reveal an important truth about persistence. A storm is not always a single peak followed by simple decline. The solar wind may remain disturbed for many hours. The magnetotail may load and unload repeatedly. The radiation belts may continue changing after the strongest geomagnetic field variations have passed. The upper atmosphere may remain expanded, affecting satellite drag beyond the main magnetic phase. Auroral activity may pulse through repeated substorms. Ground systems may experience a long period of elevated caution rather than one brief crisis. This persistence is part of why a 3-day interval matters. It allows enough time not only for arrival, but for evolution, secondary effects, and partial recovery. Recovery itself is not a simple return to stillness. After strong geomagnetic driving, ring current systems around Earth may remain enhanced for some time, keeping the global magnetic field depressed relative to quiet levels. The thermosphere may cool and contract only gradually. Satellite operators may continue to assess charging and orbit error even as solar wind conditions improve. Ionospheric irregularities may persist locally beyond the main phase. Thus, the later part of the 72-hour interval often belongs to comparison. Experts compare the measured response with model expectations. They identify what was forecast well, what arrived earlier or later than expected, and what atmospheric or technological responses proved stronger or weaker than anticipated. Each event becomes both an operational challenge and a scientific case study. This measured watching also includes restraint. Public language may sometimes exaggerate the certainty or danger of a coming space weather event, but expert practice tends to move in the opposite direction. It separates strong evidence from plausible concern. It states what is known, such as the occurrence of a flare, the launch of a coronal mass ejection, the measured speed of the solar wind, or the arrival of a shock. It also states what remains uncertain, such as the exact magnetic orientation of the cloud before arrival, the severity of local ground impacts, or the detailed evolution of the outer radiation belt. In this way, the 72 hours are not only a physical interval, they are an interval of disciplined interpretation. By the end of the 3 days, the event has become more fully understood. The Sun's active region may have rotated further across the disk or begun to quiet. The interplanetary disturbance has either passed Earth or proven weaker than feared. The magnetosphere has compressed, reconnected, loaded, and relaxed according to the driver it received. The upper atmosphere has responded in density and ionization. Auroras have expanded and retreated. Satellites and ground systems have passed through their period of greatest vigilance. Some outcomes will be clear, others will remain uncertain until later analysis. That is normal. Space weather, like all complex geophysical activity, is known first in part and only later in fuller detail. In this final main region, the event is understood not as a single terrifying moment, but as a 3-day sequence of observation, revision, and measured consequence. Experts warn because the chain from Sun to Earth is real, because modern systems are sensitive to it, and because some effects can become serious under the right conditions. They remain calm because the science depends on precision rather than drama. Over these 72 hours, instruments, models, forecasts, and human judgment work together to follow the disturbance from first detection through arrival, development, and early recovery. What began as a changing magnetic region on the Sun has become, by careful measurement, a full planetary episode observed in time. The measured interval begins to ease. The strongest fluctuations slowly give way to quieter patterns in the instruments. Solar wind values settle by degrees rather than all at once. Magnetic traces at the surface become less agitated. The upper atmosphere, heated and expanded, begins a gradual return toward its more usual structure. In orbit, satellites continue their paths through a space that is still recovering, though the sharpest pressures have passed. In the high latitudes, auroral light may linger for a time, then retreat toward the poles as the coupling between Sun and Earth weakens again. Nothing in this sequence is fully separate. The Sun remains active in its own long rhythm. Earth remains within that influence at every moment. The magnetic shield continues to bend and recover. The atmosphere continues to absorb light, particles, and heat. The human systems built in orbit and across the ground remain linked to these large and quiet physical processes. The 72 hours do not create that connection. They only make it easier to see. What remains after such an interval is often not damage, but perspective. A bright star at the center of the solar system continues its ordinary work of fusion and light. Within that ordinary work, periods of stronger activity arise, fields grow tense, release energy, and send matter outward. A small planet receives part of that outward change, not as a mystery, but as a chain of measurable causes, from the visible surface of the Sun to the charged layers above Earth. Each region responds according to its nature. Light crosses space. Plasma carries magnetic stress. Boundaries compress. Particles gather. Air glows. Signals shift. Currents move through long conductors in the ground. Then, slowly, conditions soften. The instruments remain watchful. The models continue to improve. The planet turns through daylight and darkness as it always does. Space beyond the atmosphere returns to its quieter appearance, though never to true stillness. In that steady motion, the event becomes part of the long record of observation, one more carefully measured reminder that Earth lives within the weather of a star.